Hello, welcome to NPTEL online certification course on Introduction to the Application of Artificial Intelligence to Robotics. Today we are going to talk about a very important aspect in the computer vision, and that is the object detection. Okay. And here initially I am going to discuss the basic concept of object detection, and then we will be seeing how it could be done using the YOLO. So, I am going to talk about the various versions of YOLO which are being used for the object detection. Okay, so the learning objective for the today's lectures are why the CNN is needed, okay, and what is convolution operation, what are the components of CNN, then what are the various object detection models, the multi-stage object detection model and the single stage object detection model, and then state of the art object detection models such as RCNN, the fast RCNN and the faster RCNN. And then you will be able to understand the various YOLO series. The YOLO version 1 we will be seeing the architecture and working in detail, and for the YOLO version 8 we are going to see the architecture, working and implementation, and you will be able to also understand the real world implementation of the YOLO model. So, here is the content for the today's lecture. So, in the previous lectures we have studied the artificial neural network. So, what else beyond the ANN? Alright. You see, if I am dealing with an image, right, an image consists of pixels, as all of you know, alright, and these are fed as input. For example, a 28 cross 28 image will have 784 pixels. If we are going to use ANN for this purpose, we are going to have the parameter explosion. Okay. You see, a single hidden layer with 100 neurons results in over a million parameter. Okay, and that is going to lead to the overfitting. What overfitting is, that we have seen in our previous lectures. Okay. Then we are going to have the loss of spatial context. Okay, NN can only process 1D inputs. Okay, alright, and this leads to flattening of 2D pixel grid into a 1D vector. Further, this will treat each pixel as independent feature regardless of its edges, texture and shape. Okay. Our objective here is to convert the image into a format, okay, that NN can process, okay, while the general spatial layout is not disturbed. What is the solution for these requirements? The solution is the CNN, okay, that is convolutional neural network. Okay. It preserves the 2D grid structure throughout the network. Okay. So, if you look at ANN versus CNN, so this is how we have seen the ANN, right. We have the input layer, then we have the hidden layer and we have the output layer and general ANN structure which we have seen in our previous lecture. The CNN has got actually the convolutional and the max pooling layers. So, this is our conventional neural network part here in case of CNN. Apart from that, what we have, suppose I want to recognize this number, what digit it is, okay. So, that I am feeding an input here. So, before it is passed to the ANN, okay, these are the convolution and the max pooling operations are carried out, okay. So, here the two such operations are carried out. After that, we have a flattening layer which converts this into the 1D information, and then rest of the things are same as we have seen in case of the ANN. Here, instead of connecting all of the units in a layer, okay, to all units in the preceding layer as we have been doing here in case of ANN, the convolutional network organize each layer, okay, into a feature maps, okay, and which we can think of as parallel planes or channels. Before we proceed further, let us see how this CNN has been evolved. Okay. So, the first successful use of back propagation for digit recognition, okay, that was done in 1998. Then in 2012, the AlexNet came, which revolutionized the deep learning via the GPU acceleration and large data set. Then in 2014, we have the RCNN, okay, that is the CNN based object detection with reason proposal came, as well as the popularized uniform 3x3 convolutional filters were there. Then in 2015 introduced the reason proposal network, that is the RPN, as well as introduced skip connections to train extremely deep network. And then in 2016 the real time single shot object detection, the YOLO, that is version 1 came into. Then in 2019 the optimized model scaling across width, depth and resolution came with efficient net, and in 2020 onwards we have the various versions of YOLO. Let us see what a CNN is. Okay, you see, CNN is a neural network, okay, and which is mostly used for the image processing and the computer vision applications. Okay, and it is very important from the robotics perspective, okay, as the robot has to identify the objects, okay, if it is the obstacle avoidance, so identify what objects are there as a obstacle, and if it is doing simple pick and place operation, then it need to identify which object has to be picked up. So, the CNN has got very important role in the robotics to play. Okay. So, here the input is actually the image data in the form, say, width, height and number of channel or depth. Okay. So, if it is a gray image, so you are going to have one channel only, and if it is a color image, you are going to have the 3 channels corresponding to RG and B. So, the depth is 3 for RGB image and 1 for the grayscale image. Now, the operation involved is known as convolution operation in CNN. Okay. So, the CNN consists of trainable multi-layer convolutions basically, and again what convolution operation is, that I have already discussed in my previous lecture. You see, the input image will go through several steps of feature extraction before passing it to the final layer. You see, vision is unavoidable in case of robotics, hence CNN make it most appropriate, okay, to be used. A CNN can be used for both purpose, that is for the classification as well as for the regression task. So, the core operation which we call as convolution, okay, let us see about that. So, instead of connecting every neurons, okay, we slide a small filter called kernel across the image like a moving window. Okay. So, for example, if you look at, this is my input image, okay, and of course, it has got 3 channels corresponding to RGB, and the convolution operation produces the feature map for the feature extraction, and the feature map will detect a specific pattern like edges, texture, etc., and the same filter is used across the whole image. Alright. So, that is what we are going to do, and this is how we can explain the convolution operation. Okay. So, here I corresponds to the input image and we have a kernel K, and you see, as I was telling you, this is our input image. Now, here we have the feature extraction filter, okay, which detector, which we also call as kernel. It is a Sobel edge detector. This already discussed in the image processing lecture. Okay. So, this is that kernel. Okay. So, that slide over the image. Okay. So, and in one move how much we are sliding, that is what is called as the stride. Here we have the convolution and activation, and from here we get the feature map or the edge map. And then further we could have another convolution, that we could have the feature combination, that is we have the filter 2 over here. Okay, so further reduction and non-linearity is there, and then we could have the final feature map over here. We could get the deep characteristic over here, say the face, and we can also get the object class. Okay, so coming back to this convolution operation, so this is how this is defined. Okay, here ij is the pixel coordinate, the feature map, and mn are the local coordinate of this, okay, kernel k. Okay, so this is the image and this is the kernel, and I star k, this represents the convolution operation. So, as I said, stride, it determines the step size of the sliding filter, this filter being moved over there, and there is a term called padding, okay, which essentially means that adding 0 pixels to the border to preserve the dimensions. Okay. So, next let us look at the components of the CNN. Okay. So, you see the spatial dimensions, that is the height and width, after passing through convolution and pooling layer. Okay. So, that we can get using this formula. Okay. That is the output dimension is equal to the floor of I minus k plus 2p by s plus 1, where I is the input dimension, okay, and k is our the kernel size, that is the filter which I discussed in the previous slide. You see we have input layer, it receives the image data, say 28 cross 28 cross 1, p is the padding here in the previous case, and s is the stride in this equation. Okay. So, here you see this is input layer 28 cross 28 cross 1, and then this is our convolution and the max pooling. Okay. So, we have convolution plus ReLU and then max pooling. So, this is the first stage, and then we have further one convolution 2 plus ReLU and the max pooling. Okay. And here we are using say the 5 cross 5 kernel. The convolution layer utilizes the convolution operation to produce the feature map, and what convolution operation is, that we have seen in the previous slide. Okay. So, suppose I have a 5 cross 5 kernel as we are seeing it over here, okay, and with stride 1, that is it is moving 1 pixel, okay, when this window is moving, and we do not have any padding. So, padding 0, because my input layer is 28 cross 28. So, this 28 is there, then kernel size is 5. So, this 5, okay, plus 2 into we do not have any padding. So, it is 0 divided by s stride, say we are taking only movement of 1 pixel. So, 1 plus 1. So, this is 23 plus 1. So, I get 24. So, image shape after convolution 1 plus ReLU, this is going to be 24 cross 24 into 16. So, this is what we are getting, 24 cross 24. Okay. So, 16 the number of 5 cross 5 kernel used in this layer. Then we have the activation layer. Okay. It introduces non-linearity into the network. So, common activation functions ReLU, tan hyperbolic, and the leaky ReLU. We have seen these things in much more detail during the neural network lecture. Okay. Then we have a pooling layer, okay, and this is used to reduce the spatial dimension of the feature map, okay, commonly max pooling or average pooling. How does the pooling work basically? Okay. So, it uses a sliding window with no weight, okay, here say a 2 cross 2 grid. So, this is what is used, okay, and the max pooling actually graphs the maximum value, while the average pooling computes the average of the pixels. Okay. So, here the max pooling is going to be say this one. How this happens? So, when this window is there, So what is the maximum value here? Maximum is 16. So this is 16. When this window is over here, the empty window, then the maximum value is 20. When it is over here, the maximum value is 32, and when it is over here, the maximum value is 22. Okay. So this is the max pool grabs the maximum value, whereas the average pool gets the average value. So when this is over here, so you get, see, 8 plus 16 plus 3 plus 13. So 13 plus 3 is 16, 16, 16, 32, and 32 and 8, 40, right. So 40 divided by 4, that gives you 10. So this way we can find out these numbers over here. Okay. The color coding to visualize stride is equal to 2, because one go it is passing through the 2 pixels, and for a 2 cross 2 window with stride 2, padding 0, and say C is equal to 16, my output is going to be 12. The final shape here is going to be 12 cross 16. So similarly, the shape changes to 8 cross 8 cross 32 and 4 cross 4 cross 32, okay, after convolution 2 and the max pooling. Alright, we can evaluate these numbers using the formula which I have shown previously. Okay, so note that the number of kernels C as 32, we increase C when the size of input image decreases as we go into deeper. Okay, and you can decide the number of convolution layer in a CNN, and then after all this we need to flatten. Okay. So you see, the flattening converts the multidimensional feature map into a 1D vector, okay, after convolution and pooling. So here we are doing convolution and pooling twice in this example. Okay. So this is the first convolution and pooling, and this is the second convolution and pooling. Okay, and their sizes are also shown over here. So this is the 8 cross 8 which I talked about, and this is the 4 cross 4 which I talked about. Now to convert it into the 1D vector, okay, the image shape is this one, okay, height into width cross C. So this is 4 cross 4 cross 32. So this is going to be 512 cross 1. So this is the flattening layer. You are going to have 512 inputs over there. Then we have the fully connected layer, the dense layer. This produces the final classification score, okay, and then we have the output layer, okay, and this converts final score into the probabilities using activation function, okay. So the softmax activation function is used for the multi-class classification and the sigmoid for the binary classification. Okay, so here let us go further detail into it. This was the first convolution and max pooling, second convolution and max pooling, then we have the flattening and the APSI layer and the output layer. So this is how it looks like, okay. So this is the flattened layer with 512 feature, and this is your fully connected layer, and here you have the output layer. Okay. So say fully connected layer I am taking 128 neurons, and output layer I am taking 10 outputs because my numbers are from 0 to 9. Okay. So I am doing this for identification of numbers. So I need the 10 outputs over here. Okay. So note these final 3 layers are the same old ANN, okay, we have discussed previously. Alright, and passing the input image through the various convolutions, we extract essential features while preserving their relative spatial relationship, okay, converting the data into a format which ANN can process. Okay. So to visualize how a tiny VGG processes an input image, okay, I am showing a link which you can see and you can play with it. Here you have the 3 channels for RGB, okay, and here are your convolution, and here you have convolution and ReLU here, convolution, ReLU and the max pool. So likewise you have that one, and you have the final output over here. So we can just have a visualization of this, how this is working actually, okay. So this way we can look at what is happening at the convolution, what is happening at the max pooling and so on, okay. What is happening over here, ReLU activation, okay, and then say what is happening at the max pooling. Alright. So I have already explained the max pooling operation to you. Next, let us see beyond classification. Image classification only tells what is in that image, okay, but the object detection is the next step, okay, when we need to identify what is in the image and where it is located, okay. So we need to have both the information. So the process involves identifying multiple regions of interest within a single frame using the bounding boxes, okay. So like this, alright, this is cat, this is dog, alright. So this is how we can identify. So we have the image classification, okay, where we say that what is there in the image, that is it predicts the class of the object, okay, and then we have the object localization, okay, that is it indicates location via the bounding box, alright, and this together constitutes the object detection, okay. So it locates the presence of object with a bounding box plus detects the class of the located object, okay, in these boxes. Next, let us see the type of object detection models, okay. There are two types of object detection models. These are the multi-stage detector, okay, which are region based, say CNN or RCNN. Then we have the fast RCNN and we have the faster RCNN. So these are the multi-stage detector. Then we have the single stage detector, okay, where we have the YOLO, that is you only look once series from version 8 to version 9 and so on, okay. And here is the difference between the multi-stage detector and the single stage detector, okay. So in case of multi-stage detector, detection happens in the multiple stages as the name indicates, and in case of the single stage detector it happens only in the one pass, okay. And the detection process, the proposed candidate region, and then we have the classification, whereas in the single stage predict bounding box and class simultaneously. Next, after multi-stage, let us look at the single stage detection using YOLO, okay. So you see this YOLO is designed for the real time object detection, and these days most of these object detection tools, okay, they use YOLO. Unlike multi-stage detectors such as faster RCNN, YOLO does not generate separate region proposals, okay. Here the object localization and classification done simultaneously in a single CNN pass, okay. It treats object detection as a regression problem by directly predicting what the bounding box coordinates, okay, and then the confidence score and the class probabilities. The first version of YOLO is the YOLOv8. How does it work? The first step is the grid division, okay. The input image is divided into S cross S grid, okay, say 7 cross 7, and then we have the feature extraction using CNN via a single pass, that is there, and then the bounding box prediction, okay. So each grid cell predict multiple bounding boxes, okay, usually 2 bounding boxes, and for each box it outputs 5 values, alright. So what are these 5 values? These 5 values are the XY, the center coordinate of the box, okay, with respect to the bounds of the grid cell, and then the WH, that is the width and height of the box, okay, and the confidence score. So the confidence score, that is given by the probability of the object cross intersection of union. Alright, so the intersection of union is basically ratio of area of intersection divided by area of union. Okay, so this is how it is defined. Okay, and the step 4 is the class probability prediction. Okay, you see each grid cell predicts the probabilities of each class. Okay, each class means what? Whether the object identified is a person or cat or dog, okay, of the object present. Alright. Then the output tensor, the fifth step, okay, that actually what we get here is S cross B cross 5 plus C. Okay, so that is what we get at the output tensor. Okay, so you see in this one the first 10 numbers are corresponding to what? Bounding box 1 and bounding box 2, because one bounding box you need the 5 information, right? X, Y, WH and the confidence score, this one, right? So for this is for the one bounding box, right? So for the two bounding box, okay, we have the 10 number and rest are the class probabilities. Okay, then we apply the non-maximum suppression. Okay, you see as multiple grid cell might detect the same large object, we are using the two grid cells, right? So out of that, which one is having the maximum score we keep. Okay, so the original YOLO has used 7 cross 7 grid, B number of boxes 2 and C as 20, and YOLO predicts 7 cross 7 into 2, that is 98 bounding boxes at the same time. Whatever I have discussed in the previous slide, that is represented graphically here for the YOLO version 1. So you have the image, it is divided into a 7 cross 7 grid. Then this is passed through the CNN, okay, for the feature extraction purpose, and then we have the bounding box prediction over here. Okay, so these 5 numbers will come, X, Y, WH and the confidence. Then we have the class probability prediction. So in the YOLO version 1 they had the 20 classes. Okay, so C value was 20, and then after this we have the output tensor. Okay, so it's a 7 cross 7 cross 30. How this 30 came? We have the 20 classes and the 2 boxes, so 2 into 5 plus 20, so that number is 30. Okay, so this is how this 30 comes, and here you see initial 5 is for the box 1 information, then next 5 are for the box 2 and others are the class probabilities. In the step 6 we have the non-maximum suppression and the final detection. Here we have the 49 cells, and in the final detection we are indicating the boxes as well as the class label confidence. Okay. So the YOLO version 1 architecture, you see the input image is resized to 448 cross 448 cross 3. So this is that 448 cross 448 cross 3. Okay, and the backbone is inspired by Google Net. Okay, so you have 24 convolutional layers and 2 fully connected layers used for the feature extraction and prediction. Okay, so you see as you move right here, the network reduces the image spatial resolution while increasing the feature depth from 3 color to 1024 feature here. So you see here we have the 3 color and here we have the 1024 features. Okay, and then alternating filters are used, okay, for the dimensionality reduction. Okay, that is 1 cross 1 filter and 3 cross 3 to learn the complex features, and the fully connected layer gives you the final 1D vector over here. I am not explaining all these process, it is a self explanatory. You can use the formula which I have discussed in order to get these sizes. Okay, so and the final vector is reshaped into the 3D tensor, that is 7 cross 7 cross 30. So this is that the final vector, okay, with class prediction and the bounding box coordinates. So this is how the YOLO has evolved actually. Okay, so we had the version 1 to version 8. Okay, the first real time single stage detector was there, then version 2 the anchor boxes came, Bayes normalization, better accuracy, version 3 multi-stage prediction using feature pyramid. Then we have the version 4 where we had the improved speed accuracy balance, okay, with CSP darknet that was there. Then we had the version 5 easier training and practical deployment, version 7 optimized real time performance, and the version 8 has the anchor free detection, improved accuracy and the flexibility. We will discuss the version 8 in the upcoming slide. So, version 8 was developed by Ultralytics in 2023. It is a key improvement in the YOLO version 8. What are the key improvements? Anchor free detection is there in this one. Decoupled heads are there, okay, which means you could have the classification and bounding box regression, they could be done independently, okay, and then they use the C2F module basically, okay, which enables improved feature extraction that help network learn richer visual patterns while keeping the computation efficient. The C2F feature that is there, and the feature fusion for multi-stage detection. These are some of the features of the YOLO version 8. Okay. So, you can take a look at the architecture, although it is very complicated, provided link for that. Okay, so this is the architecture. Here you can see that it consists of many C2F blocks, and here the details of the C2F blocks are given, what all it contains in it. So, the YOLOv8 architecture have the backbone, that is the feature extractor. It extracts important visual features, okay, from the image using convolutional layers. Then deep layers for the complex features are there. Okay, it uses C2F blocks to learn feature efficiently. So, this is how it looks like. So, you have the input image, backbone, C2F and the convolution. Then you have a neck here, okay, and head anchor free and the decoupled as I discussed, and then you have the classification and the regression bounding boxes. Okay, so the neck feature which I have discussed in the previous slide, this one, okay, that combines information from the different layer of the network, okay, it merges fine details from earlier layers plus semantic understanding from deeper layer. This help YOLOv8 detect small objects, large objects and objects at different scales. Okay. So, the head, that is the prediction layer, predicts what? Object class it will predict, the bounding box coordinate it will predict, and the confidence score it will predict. Okay. You see, just discussed, it uses the separate classification and localization, and there is anchor free detection, okay, for simpler and more flexible predictions. So, if we look at the implementation of this, okay, so here are the key lines from the YOLOv8, okay. So, we import YOLO, okay, then we load the model, define the input, okay, and then run the inference, okay. So, I have provided a link over here. So, this link we can just check. Okay. So, you see, this is the input image. So, we have the YOLOv8. This I have opened in the Colab. This is the input image, and in this image, say I want to identify this bus, I want to identify the person, I want to identify this stop sign. Okay. So, all this we can do. I can run this code, okay, and we have the output over here. So, you see, this is what the output is, okay. So, it identifies the objects, the person with the box, the bus, the stop sign, okay, and it gives the confidence score. This is the implementation result I have shown in the live demo over there, okay. So, it shows, say, the object, confidence score, and it also shows the coordinates, right, x, y coordinate, width and height, okay. So, the bus, person, 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 person and the stop sign. Let us summarize today's lecture. We have seen the limitation of ANN to deal with the images. So, came with the CNN. okay, and it uses the convolution operation, okay, to prepare the feature map, and image classification using CNN only tests the image, okay. So we have to know where the target is located, we must use the object detection module. Again we have the multi-stage and single stage, as we have seen the multi-stage in multi-stage RCNN, fast RCNN and faster RCNN, and for the single stage we have seen the YOLO, okay. So various versions of YOLO I have explained in today's class, and you see YOLO treats object detection like a regression problem, okay, and simultaneously predicting the bounding box coordinate, the class probabilities and the confidence score, and there are many series of the YOLO has come up, okay. So these are the some of the references which we have used in creating this lecture, and thank you. See you in next lecture.